Hope you all have a good refreshment. So let's pick up from our coffee break. At the coffee break, we wanted to start with the topic of what is capacity. So what is capacity? What is capacity? Namba?
It's an amount of reaching some suitable
It's an amount. Continue.
reaching an amount of I forgot the English word.
All right, anybody else? What is capacity? Yes?
Possible quantity of something.
Okay, a quantity of something. Any suggestions?
Some object or some, I don't know, maybe of action.
Action. Yes, in the back.
It's the ability to provide access to something during the specific period of time.
Ah, time. Time and the possibility to provide, what did you say? Access. So access over time. So yes?
Can also be available space.
Space. Time and space. In the Starship Enterprise. Yes. Yes. So good. So access over time and space. So capacity, quantity and amount. What is the capacity of this classroom?
100 persons.
100 persons. I have a suggestion of 100 persons. And
Should it be suitable or should it
and is that time and space? What about time?
how long time will it be?
How long we can breathe, how long we can keep breathing. So there's a time component, because do you mean a stationary capacity, or do you mean a capacity, a cumulative capacity, as we use the resource? So the word resource is important. What's a resource? Sorry? Resource? What is a resource?
How much we will have to work with?
How much we have to work with? So a resource is something we will consume. Is something we will make use of. So we have natural resources. We have water, air, and wood. We have physical, man-made resources. In this class, the resources we're talking about are track, rolling stock, labor, crew labor. So resources. So capacity, we have access over time and space, and we are using a known resource that has a dimension and has an amount. And with all this, there's, in some of the literature, supposedly a confusion over what capacity is. But I would argue to you there is not a confusion. In some cases, there's just a failure, unwillingness to commit. An unwillingness to commit to a known definition for capacity. So capacity, so let's take a look here. Let's talk about capacity. So show you what I think about capacity. So we're going to talk about capacity modeling. And it's important to define what capacity is, because if we don't know what capacity is, we can't model it if we don't know what it is. So we want to define what we're talking about in capacity, particularly for a railway line, for transportation, because we're talking about railways in a railway class. So we're going to talk about the measures of capacity. And I'm also going to speak about these in national terms, because it is a fact of life that there are very different ways of viewing the business enterprise by nation. There are very different ways that North America does business accounting from the way Europe does business accounting. There are actually differences of opinion about how things should be counted on the books between European businesses and North American businesses. And there are different ways that these things are done. And there are different ways of measurement that are considered a priority in North America for railways and in Europe for railways. So we want to be aware of that. We'll talk about theoretical approximations, parametric measures mostly, simulation, and then mathematical programming, which we've already really covered, so we really won't talk about that a great deal because we had a whole class on mathematical programming a couple of weeks ago. Last time, most recently, we got our grounding in the track infrastructure. So we know about our resources. We've talked about this. We know about track. We know about train equipment. We've just done a homework assignment where we were calculating the cost of resources. And we talked about signals, and we talked about train running time over the infrastructure, over the resource. So these are foundation pieces that we've already got to build to go forward in capacity modeling. So today we're going to go through parametric measures. We'll talk about headway measures, train path measures. We'll talk about simulation. I'll give you some nice pretty screen pictures of simulation products for capacity modeling. And then we'll quickly review optimization. We've already covered this again, as I said, so we're just tying this topic into today's conversation about capacity modeling. What is capacity? Capacity is the capability to support traffic. It is the capability to support traffic. Traffic over a known resource, over a known piece of time, and then space defining the geography for us in transportation over a certain distance and geography. Time, space, and resource. What traffic can that support? That is what we're concerned about in capacity. The problem is traffic has two fundamental components. Not just transportation traffic, but any business enterprise. If you go study operations management, if you take a hike across campus to the pretty building that DTU management has, you will study operations management and you will once again learn that business services have two dimensions, volume and robustness. And they are constantly at war with each other. They are conflicting demands very often. So we are interested in transportation traffic, and we will see that there's a volume measure and a robustness measure. Volume is flow, it is the rate of flow, it is the traffic, it is how many trains can I get down the track.
So limitation.
Sorry?
So it's called limitation?
Traffic is an output. It's not a limitation. It could be constrained. We will find that there is an upper limit to our capacity. So there is an upper limit to our capacity. There's a hard physical limit. We can see various configurations of resource and time that do dictate there is a hard limit to that capacity. We are going to measure that capacity in terms of the count of trains, the volume. And if you get really economic, really supply chain oriented, you might say, oh, what if I make a bigger train? So I have the same number of trains, but now I have more volume because I'm carrying more freight, I'm carrying more passengers. Double-decker passenger train, stuff like that, double-decker car, superliner. Robustness is the quality of the train paths. So we can get a lot of flow through the line, but if that flow is with a lot of station stops, or that flow is with a very bad travel time for the customer, or if that flow involves inconvenient travel times, or if the punctuality of the flow is really bad. If we have a high average flow, but our variance, our timekeeping is really bad. That is, we have a very high variance, we have a very high source of error, we have a very high probability of delay at the stations or en route. That is a robustness measure that we are making worse. That we're getting high variability means bad robustness. And so that's another measure of capacity. And the reality is that the two continents, the two different ways of thinking about capacity have basically followed these two lines of reasoning. And they are rooted in legacy thinking, they are rooted in historic precedent, they are rooted in fundamental assumptions about the economics of rail transport and the services provided to the customer and how we're going to drive this thing. And so in North America, the fundamental measure of capacity is train delay. You go on a business call, you go on a meeting with somebody from Union Pacific or BNSF, you go to a conference, you go to a discussion with anybody from North America, and you start talking about capacity, and they're going to start throwing numbers at you like, how many minutes of train delay per mile do I have? How many delayed trains did I have yesterday? That's their measure of capacity. The delay, they are focused on delay as their measure. They are implying that all of the delay is a reduction in capacity because we are slowing the trains down, and if I slow the trains down, I'm reducing my flow, Little's law. Longer travel time must mean that the flow is going down if the capacity stays the same, if the inventory stays the same in Little's law. In Europe, it's all about measuring flow, because in Europe, the presumption is that we are on time. There isn't going to be any delay. We're all running to a timetable. There is no delay. This is the timetable. The train's going to run to this timetable, and there's no argument, there's no discussion. This is the timetable. Platform 2, 1352, stand there. The train's going to be there. So with that assumption, then, we are all counting train paths. We are counting rates of flow in our conversation about capacity in Europe. We're counting train paths. And you see that in the conversations people have, and you see that in the way the software generates results and the way the software generates output. Here is a sample output for North America. And I chose this because just to reinforce this, you look at this table of data, and it's all about delay. It's like, how much delay do I have? How many delay minutes per 100 train miles do I have? This is a very typical kind of management report for North American railway system, because this is where they're focused. This is what they're all about right there. Little's law again, right? Let's refresh this. We've talked about this before. Inventory equals flow times time. So now we're going to flow this around. So we're interested in capacity. So we're going to say capacity is flow. Capacity is a rate of flow. How many trains per hour? How many trains can I get down the railway line per hour? It's going to be a function of how long does it take the train to get down the track, and how many trains can the track hold. That's my capacity right there. And very often, time delays mean time gets longer, time gets worse. So North America is looking at this and saying, hey, we're going to keep this time tight, squeeze this down, no delays. We're going to call that crew in that just delayed the train for an hour. We're going to, quote, call them on the carpet, is what they say in North America. Call them on the carpet. What does that mean, call them on the carpet? Yeah, it does, but why is it call them on the carpet? What is it about the carpet? See, it has no meaning here in Denmark, because there's no damn carpet anywhere. I miss carpet. I really miss carpet. The hardwood floor is just getting a little old after a while. Where's the carpet? Call them on the carpet. So you're a train crew. Yes? Yeah, exactly. Right? Right? You're a train crew, and you're wearing boots and overalls, and you're greasy and you're dirty. And the executives up in the boardroom have carpet in their offices. And so if you get called on the carpet, you're being called up to headquarters to explain yourself. What did I do wrong? Getting called on the carpet. All right, so you got to explain the time delay, because this is the function North America cares about. But in Europe, this is assumed under control. This is under control. So in Europe, we're about how many trains can I pack into the network? And we focus on the track diagrams, and we focus on the station diagrams, and we focus on allocating trains to platforms and stations. How many trains can I pack into the station? Well, that's inventory. The more inventory I got, the more flow I got. How wide are my blocks? Let's make more signals. Let's make more blocks. I can pack more trains on the network. Increase my inventory, more flow. So, time-centered, resource-centered. This is where we're at. This is where we're at typically in this conversation. It's changing because some things are starting to merge. Europe is trying to reinvigorate freight transport. That means talking about longer freight trains. That means some major changes to the network. North America has a very congested network, and is no longer can focus only, at least in the research that I have argued, can no longer focus only on delay as a measurement of their dispatch and of their rate of flow. So let's talk about parametric measures. We've kind of mentioned this before. I've used the word parametric. These are various rules of thumb. We're going to fit these things to statistical data. There are a couple of key players in this conversation. You can find more, but these are the ones that I have argued are kind of the benchmarks, the touchstones of our history of railway engineering here. This guy, Procopy, I'm probably not pronouncing it correctly, but he goes back, way back. This is one of very often cited measures of railway capacity. And again, this is a parametric measure, and he's taken some statistical samples of data from real operations and fitted it to a function. And we are using something that is really very much kind of like Little's Law here. We have a placeholder for inventory, and then we are manipulating time and rate of flow here in these equations to get a view of where we're going with our capacity. And then we have the International Union of Railways. So that is French, right? So that's Union International Chemins de Fer, something like that. That's our international union right there. And so back in the 1970s, they're really focusing on flow. They're focusing on headways, and they're focusing on ways to measure how much flow they get, not really getting the full measure of capacity in terms of Little's Law. So we move forward in time here, and again, we're still looking at flow. There's a little bit of an implied inventory with Kruger here in this equation, but this is significant in that he is trying to look at two-way directions on track, because we have single-track railroading in North America. Kruger's a Canadian guy, Canadian national, and he's concerned about single-track railways, so his function has a provision for opposing traffic in his estimation of capacity on the line. And then we have Packel here, a European guy from Germany, I think. And again, if you look at his, what's called, quote, the exploitation rate for the capacity of a line, if you look at that, it really is a function of Little's Law. Again, we have time, flow, and an inventory, which is implied by this exploitation rate. This exploitation rate implies a certain number of trains packing the network, a certain amount of inventory of trains on the line. And then finally, the UIC 406 method. This is really kind of state of the art in terms of how people visualize capacity calculations in Europe today. This idea, fundamental idea, is timetable compression. And the key word is timetable. You have to have a timetable before you can use this. Most railroad traffic in the United States does not run to timetable, so this is totally irrelevant to North America because we don't have a timetable in the first place. Most train traffic in the United States is randomly dispatched, like a taxi. They line the trains up in the yard, and they look for a clear slot in the track, and they say, go. And the train pulls out, and you cross your fingers and hope it gets there. And seriously, I mean, because I'll tell you why. I'll tell you why. Much of North America, it's getting better. It's getting better, especially on high priority lines, lines like the racetrack, the Transcontinental Corridor and the BNSF, that's Los Angeles to Chicago through New Mexico. That's a racetrack. It runs intermodal trains. They run like streetcars. You can stand up on a mesa. I've done this. You can stand up on a mesa and look out for miles across the Breaking Bad territory of New Mexico, and you can see the BNSF main line, and you can see multiple intermodal trains running in the signal wake of each other out in the heat of the desert. You know, 3 or 4 intermodal trains, each one of them like 70, 100 cars long, following each other with a 2-block separation along the track. And they have to really hustle, because that's all that container, all those Christmas lights from China coming to Chicago. They're coming by container. They're unloaded at Long Beach, Los Angeles. They go onto a container train. They go to Chicago, and then they go to Walmart. And that's how we get all the consumer goods in the Midwest so cheap. So they're getting more picky about this kind of stuff. But they really still manage a flow. Tonnage-based railroading is what it's called, tonnage-based railroading. Tonnage-based railroading says, I'm going to store freight cars in my yard. I'm going to store up freight in my railway yard. And when I've got enough tonnage to make an economical train, I will call a crew, literally call a crew on demand. Railroad crews in the United States work on demand. They do not have a schedule. They wait at their home for the phone to ring, and then they go when they're called. Call a crew shows up, couples up the locomotive, tests the air, and away they go. And you have all kinds of issues where if you're tonnage-based railroading, it means you're minimizing the horsepower ton. It means you have trains that just have enough horsepower to just basically make it over the highest grade profile on the line. And what happens is you have a bad rainstorm, you have a miscalculation, you have a flat wheel, you have a locomotive with a turbocharger that's acting badly, and now suddenly a train stalls on the hill and you have to double the hill. You back the train up, you cut the train in half, you bring the train up the hill in 2 pieces. And you do that, and you've just locked up the whole network for 3 hours behind you. So that creates a lot of variance. Now, they're getting better at that. They're doing a lot to really stop doing that. I mean, that doesn't happen the way it used to. A lot of operations research techniques are being applied to doing things like, let's not make that happen anymore. More carefully matching locomotives to train size, more carefully managing these kinds of things. But the reality is, in North America, we are still running a tonnage-based railroad, and that does lead to a lot of variance and a lot of delay on the network. So anyway, UIC 406, Europe, we're going to compress this timetable. We've got a timetable. We have our train paths. There's our track network right there with some signals showing the blocks. And this is in this particular case, we have a 2-directional track. We have a 2-directional track. The signals are facing both directions here. So we have, just for argument's sake, let's say time is going up this way. So this is 9 a.m., 10 a.m., 11, 12, 1 o'clock, 2 o'clock, 3 o'clock, et cetera, et cetera. And so this train is going that way on the track. This train is going that way on the track. But this train is going the other way, is going down this way. And these are what we're going to see here in a few minutes. These are called the block occupations. And so the idea here is this is the timetable for the track network. And this boundary, this edge and this edge here, are the total amount of time occupied by these trains on the network at this point in the conversation. And what we're going to do is then manually, or with the aid of some software perhaps, but essentially just redraw this picture and squish these paths together until they're touching, until they just bang up against each other. And we're going to ask our question, how much time on the network will these train paths consume if we squish them all together into the tightest pack we can get? Measure that, which is this lowercase k right here. How much time do they occupy on the network when they're completely pressed together, as much as they can be safely? And then we have our utilization of the network. So the UIC 406 is not really a capacity measurement in the sense of a quantity or in the sense of what is the rate of flow. It is a utilization measurement. So it says, what % of the resource am I utilizing? How efficiently am I utilizing my resource with this particular timetable or with this particular track configuration? We will spend more time on this. After the coffee break, we will have some exercises and we will look at this again in some more detail. But it really is pretty much just exactly what I just told you. You know, you can have better tools, you can have things that automate the process for you, but if you got enough time, you can do this whole thing by hand on paper, just like I just demonstrated. So those are parametric methods, equations, manual methods to kind of estimate the consumption of the track resource. They are all static. I'm going to back up a second here. Static, 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 static. The answers don't change. I can go through these slides 5, 6, 7 times, but the answers don't change. The answers are all the same because I put some numbers in and I give you an answer out and we're all done. We go home for coffee. But the reality, of course, we know is, as I just described with the tonnage-based railroading in the United States and in Europe, little things like little old lady gets stuck in her wheelchair at the entrance to the coach and suddenly the train can't pull out of the station, stuff like that. We have variance. We have random delays. We have weather. We have service issues, we have breakdowns, we have random delays. And so now we want to measure the capacity of our network for its robustness, for its ability to carry traffic, within a certain boundary of robustness, a certain boundary of reliability. And to do that properly, we then do need to use simulation. We need to randomly sample patterns of operation and evaluate how the network responds to variation in inputs, variation in weather, variation in trained behaviors. And so that's where we get simulation. Those of you who may have had some prior experience in, quote, simulation or discrete event simulation is what we're really talking about. These are all various simulation tools specific to railways. They are discrete event simulation tools specific to railways. Canadian National in North America is the leader, the innovator in this back in the 1950s. Way back in the age of the mainframe computer, the IBM mainframe, Canadian National started writing simulation programs to simulate the traffic that they had on a single track railway across the Rocky Mountains in Western Canada. And so they were leaders in this. And then more recently, we have this company called Berkeley Systems in North America that is pretty much the de facto standard for simulating North American railway track operations. And then OpenTrack is another method that's the kind of a big standard here in Europe, although there's more competitors in Europe. In Europe, we have a few more competing companies doing this kind of thing, but OpenTrack is a very good example. How do they all work? They're all very similar. They have to have some kind of user interface for defining the track network, some way of inputting data into the system that says, here's the track, here's where the signals are, here's where the blocks are, here's how fast the locomotive can accelerate. All this information has to be put into the network, and then we define for the simulation, what trains do you want to run on this network? What kind of schedule do you want to run? What kind of pattern of service do you want to run? And then we want to simulate the train movements. What does that mean, simulate? For those of you who don't know what that means, it means we have a train, we have a process that's going to run, but we know for a fact that this process is subject to random variation. So we are going to input into the simulation software the formulas, the statistical formulas for the distributions, the random probability distributions of the things that might happen that are not specifically known, that are random. And then we're going to tell the software to run a game, almost a game interface. We're going to run a game of the dispatch for a day, and we're going to randomly sample things that could go wrong with those trains and fit them into the pattern that the game is simulating of the train movement. We're going to collect the data from that run, write it down in the database or in the computer software. We're going to back everything up, and we're going to do it again. And the software is going to pick a new set of random numbers that simulate the various things that could happen to this train and do it all over again. And the software is usually going to do this hundreds, thousands of times, and then aggregate all of these results from these random samples and give you some kind of statistical picture of, here's what I think is likely to happen with this rail network over a variety of possible outcomes. So let me show you what that looks like. Of course, here I mentioned to you already Canadian National. We've talked about this signal wake model. I've talked about this in terms of signals and in terms of run speed. But again, you can look in the quoted literature from the guys in North America, and they're really focused on delay per train mile. And so how are we going to do that? Berkeley Traffic Controller. I'll just jump straight to the fun pictures here. So here's Berkeley Traffic Controller. This is actually one I drew because I used this once for a little bit of research, and I still may in the future. So this is a very long single track line. And it's not clear from the picture, but it does actually loop all the way around and connect like this. And these are sidings, and then these are the signals. Here are all the signals right here. And you can actually define the actual physical track network in Traffic Controller and tell it physically where is all the stuff. And you can tell it what kind of switches are they, and are they manual switches, are they electric switches, what's the curvature on the switch. All this stuff you can put into Rail Traffic Controller. You can tell it, and then you can tell it, okay, SD40 diesel locomotive, 6-axle power. How fast can it go through a 20-degree curve? How long does it take to clear the switch? How many feet does it have to be before it's in clear of the switch and the points are open? All this kind of stuff. You can put all this into rail traffic controller. And then we tell rail traffic controller, oh, I want to run a whole bunch of coal trains. I want to run 12 coal trains, and I want a general mixed train, and I want to run an intermodal train, and I'm going to set that all up in the little kind of, quote, timetable. It's not a timetable like you understand a timetable. It's just a wish list of trains I want to be running on this network. And rail traffic controller's big selling point, its big feature for the North American market, is that its engine is designed, its calculation engine is designed to emulate the behavior of a human dispatcher under North American service. So you say go, and it lines up these trains for their departures, and then it starts simulating things like, this locomotive just had a brake failure. This train got stuck on wet leaves, and it can't get up the hill. This train is running slow because there's something goofy going on with its diesel prime mover. And it simulates all that, plus all the interferences on the single track line, and where are we going to meet and pass the trains at the sidings. And it simulates what it believes the typical human dispatcher, because most traffic in the United States is dispatched by human beings in a dispatch center, and it still is true in Europe too. How will the dispatcher plan that dispatch? And it simulates that. And then what we have here is a graph that traffic controller generates while it's running the simulation. And it actually generates this graph. This bit here is the warm-up cycle, where it's just warming up the random number sequence for the simulation. This is the actual sample period for the run, quote, of the simulation. And then this is the cool down at the end of the simulation. So this is really where the data is collected from. And this green stuff right here is what are, quote, the dispatch conflicts that are resolved. So rail traffic controller starts plotting out the positions of the trains. And then when it sees a conflict that cannot be resolved, it backs up its decisions and picks a different plan. And this is meant to emulate what a human dispatcher would do in North America. A human dispatcher would start planning out their moves, probably on paper, probably using a string line diagram in a book, plan out their moves, and then keep, with a rubber eraser, kind of back it up and change it again and see which way you can get the trains to go to get the traffic through the line. And so this is actually where the rail traffic controller is testing different alternatives and then looking for ways to reroute the trains, like a human dispatcher would. And it's primarily concerned with something called lockup, which is a big, big deal, especially in single track railroading. But it can also be a problem in double track line too. Lockup is a situation where you have dispatched a pattern of trains, and the trains get to a position, we start here, and some guy makes a bad mistake, and he allows this train to come forward before this train has made its path through. That train is now there. This is lockup right there. There's no way for this network to go forward without a train backing up. Not something you want to do. Not something you want to explain when you are called on the carpet and you have to explain why you gave an instruction to the conductor of a train to back his train up on the network. So lockup, you want to avoid that, but it's you know, like painting yourself into a corner, to use another English expression. You don't want to sequence the trains in such a way that you suddenly discover you have no way forward. You have no way to unlock this Rubik's Cube of combinations of train paths. And this can be especially difficult on single track network, where you have trains going opposite directions, and it's not as simple as just saying, I'll just wait till the traffic in front of me gets out of the way. Well, there is no traffic in front of you, get out of the way. This is a clear lockup right there. So, and you can still have issues like that on a double track network. You could have a problem where if you're not careful, you know, this guy moves to that position, and now you're kind of, it's not quite a lockup, but it's still a very bad slowdown, very bad blockage on the network. So anyway, you run rail traffic controller, and it will generate in its output a string line of all the dispatches that it did for a period of time. And then it will generate statistics on the run, and of course, what do we care about? Delay per 100 train miles, because we're in North America. This is what we care about. So rail traffic controller gives you these numbers. Now, to compare that, we have this product called OpenTrack, which is a very popular, well-adopted software package for Europe for the same purpose, simulating the dispatch pattern, simulating the timetable of trains. The difference is that the key word is timetable. So OpenTrack really is focused on, I have a timetable and I'm going to follow that timetable. So it's much more focused on keeping to the timetable and trying to return to the timetable after a disruption has happened. And it also is much more focused on modeling the actual specific block occupations. And you can see it in the output screens of OpenTrack and the kind of reports it generates. For example, OpenTrack will generate a Gantt chart. A Gantt chart is a resource occupation chart. It will generate a Gantt chart. These are tracks. And then these are occupations of the track. This is time. And these are occupations of a piece of track over time by trains. And the little top bar is the physical occupation of the train on the track. And the longer bar below it is the resource occupation based on safe signaling instructions. And we'll explain that here in a couple minutes. And then it also has these charts where we see the runtime efficiency. It generates charts that show you what is the allowed runtime on a piece of track and what is the train actually physical of accomplishing. What is the train actually possible to accomplish within these limits? And you can see here, we got a real problem because even though this track allows 140 kilometers an hour, this little bit right here kind of is a hard constraint, you might say. And the train has got to slow down right here to meet this lower speed limit on this track. So it possibly might be able to kind of go up like this and get to here and come back down, but it's almost completely wasted energy. It's all fuel burned to get it up to speed, only to have to put the brakes back on right again. So this is an area where we have a low efficiency because we really can't use that speed. That track speed is not really available to us. It's not really realistically possible to use it. And the same thing right here. We're really not going to use this. So this is an example for an analysis where you might say, hey, do we really want to maintain the ballast and the rail on this piece of track for this extra little bump of speed? Or should we just drop the speed down? Should we just go ahead and back up and drop the speed down, save us some money in maintenance, maybe retime the signals for that lower speed? A lot of decisions like that could be really studied in detail with a diagram like this, which isn't quite so important in North America because, you know, when you're running an intermodal train across the New Mexico desert, you don't see a lot of this. You know, it's like open the throttle to run 8, put your feet up on the dash, and, you know, wait an hour, and then maybe you'll get somewhere. So OpenTrack. And then, of course, mathematical programming. We've covered this in depth already in a previous lecture, so this is just kind of a recap of the topics that we've already covered. So how does mathematical programming fit into this? Well, mathematical programming allows us to say, I have a resource, I have constraints on my track network, and I will code those constraints into the mathematical program saying how much track do I have. And then I'm going to say how many trains can I pack into that resource in time and space. So a lot of the mathematical programs that I've already shown you in previous lectures are basically a formulation that says, how can I maximize the number of train paths given a constraint that I got this much track and I got this much time and I got this much stuff going on. We've already seen formulations that are focused on delay minimization, again, addressing the North American concern. Much of the stuff that you will see further in something called the Burlington Northern ARIES case study, which we will be doing in a couple of weeks, based on this formulation. A good friend of mine, Edwin Kraft, was with CSX for years and years a while ago, and he's published a lot on this stuff about jam capacity. How much can you press into the system before the robustness just goes off the charts? Southern Railway had a huge, actually implemented, one of the few instances where they actually implemented it. Southern Railway in the United States, this is in Atlanta, Georgia, actually implemented a linear program in their dispatch center with an IBM mainframe computer, and they were actually doing dispatch planning with linear programming, but it didn't last very long. They had a merger with another railway and management changed, and they said, never mind, we're not going to do this anymore. And then network packing. So this is all the European guys, mostly, except for this strange guy right here. But mostly European stuff. We got a Swede, we got an Australian, we got an Italian, you know, lots of European guys, kind of other side of the ocean kind of guys, all concerned about how many trains can I pack into the network given a fixed infrastructure? And, oh, by the way, I'm going to run with a timetable. And then this is a whole crowd. This is closer to home. So this is our folks down in Holland, in Amsterdam, and they've been doing a lot of this. And they actually received an award, a very prestigious business school award for their work in designing the railway network in the Netherlands. This award was 2008, I think it was 2000, you don't remember? 2008, 2009, something like that. They actually received an award from the Informs, which is a major operations research management science group. And this is periodic schedules, and they are using linear programming to design periodic time schedules for high density passenger services in their typical network. So in conclusion, we have delay and volume. And the delay and the volume are both representable in Little's law. They're both elements of Little's law. And we're basically saying, how do we balance volume and delay to get the capacity to make use of the capacity of our network? And the capacity of our network in many ways is essentially a measurement of flow, but it's also limited and constrained by the inventory of the network. How many trains can be on the network at the same time? What are the resources I have to support the holding of trains in time and space that then allow me to have the flow that I'm looking for? We've gone through a whole bunch of analytical estimates, parametric measurements that really in many ways can be seen as representations of Little's law. Simulation is the big gorilla on the block right now. Most every major national railroad uses some commercial simulation product to really settle once and for all their discussions about can we take this service or not. And optimization is the new kid on the block, really speaking. Optimization, lots of papers published in optimization, a few examples of optimization actually in application, actually in use, but more and more likelihood that we will see this in the future as this filters through your training and you go out into the career in the railway companies, and as the computer tools become more user-friendly, that we're able to provide these kinds of solutions in a user-friendly way. So thank you very much. Any questions? Eric?
What do you consider delay?
What do I consider delay? So delay per train mile. So in the United States, delay means the train stopped. Because yes?
The measurement, 88 minutes per 100 minutes.
Per 100 train miles. Train miles. 100 train miles. So if, because the manager gets a report from the network, say Burlington Northern Santa Fe or Union Pacific, and the network is thousands and thousands of track miles all over the place. He's got hundreds of trains running each day. He's got to boil that down into a statistic, and so they'll sum up all of the delays that trains experienced over the whole network and divide it by the number of train miles they ran, and then report that as a statistic, as an operating statistic. And those train delays could be held at the yard for lack of a crew, stopped at a siding for a meet for some reason for a couple hours. Broken coupler, happens quite often. Broken coupler, train ties up the line for a couple hours while they replace a coupler. All kinds of stuff like that. Accidents, just slow travel due to bad weather, due to running out of fuel. Train runs out of fuel. Does happen. Stuff like this. Yeah, and you sum up all those delays and you say, hey, what's going on here? Why did we have these delays? Great. All right, another coffee break, and then we'll come back for some exercises. Thank you very much.